Oh no. Okay, we're ready to begin. We're now at lecture 6A, and it may take 6B to also finish this, but we started in 5B, constructing functions, and I wanted to identify there were three types that I was going to expect you to be responsible for: your geometric figures and your solids. And if you look back at 5B lecture, I brought in our Math 131 textbook, because it did a little better job reminding you of some geometric figures that you studied in your geometry classes. Your rectangle, you've got an area and a perimeter. These are your two geometric figures. And your circle, area and circumference. And then you want to work on some solids. These are called solids. You have a box. Your volume, as you know, is length times width times height, which is really just the area of the bottom of the box. That's xy times the height, z. And of a can, or called a right circular cylinder, we'll get the area of the circle, which is the bottom, pi r square, and then multiply it times the h. So these are the geometric figures and the solids. And then, oh, was it lecture 4?
Last lecture was lecture 4.
I'm on the wrong lecture.
I mean, it's the right stuff with the.
5. Are we on lecture 5 or 4? 5. I'm wrong.
5.
Woo! Thank you for correcting me. I did this last time, and therefore I didn't know what I was doing, did I? Didn't realize I was working ahead. Thank you for getting me straight. We're on lecture 5A, not 6A. All right. And then the demand equation. I want to look at that. We're going to look at it directly from a calculus book, so you see how it's used there. And then we're going to look at the cumulative review that I ask you to work out in great detail from page 295. We'll look at some of the problems there and look to correct. And then 3.1, move on into quadratic functions and their applications. Actually, some of the applications in section 3.1 come back from constructing functions. So that'll be a nice little double dose of the same concept. But here we're just practicing. Here we're going to actually go a step further and find the maximum or minimum value of a function. So we'll be working from there. Alrighty. At the end of lecture 4, we had looked at our little chicken pen. We were the rancher. We had a rancher. Remember, I brought in some 131 problems to show you how these problems move right on. And actually, in section 3.1, we're going to go back and work this particular problem because we will be able to, even without calculus, to do that. We had 100 feet of chicken wire. One side was against the barn, and we were interested in maximizing the area. So if you look back in your notes, we drew that. Okay, so that was one of our geometric figures. That was a rectangle. Let's go to problem number 2 here. And again, you have similar problems in your textbook, but I thought if you work right off Math 131 exercise for calculus, you'd see for sure this is really important stuff. Okay, number 2 says find the volume of an open box with the greatest volume. Now, we're not going to learn how to find the actual dimensions in this class to give us the greatest volume, but we're going to learn to set up the function, and that's our goal. So we want to talk about a volume of a box. It's open. That can be made from an 8-inch by 15-inch rectangular piece of sheet metal. And we're going to cut out squares, equal squares from the corners, and fold it up. Okay, so we got two things going on here. We have a rectangular piece of metal, and we're going to just go back to the good old days of playing. We're going to pretend that this is an 8 by 15-inch piece of metal. And what it says is we're going to cut out square corners and fold it up and make a box. So just to get a visual on this, I'm just going to fold the paper over. This is so you can entertain somebody on Saturday night and show them how to make a box. Free entertainment. Okay, and this is really metal in case you don't believe it. I'm just really strong. I just cut out a square corner. This was my piece of paper that I now have square corners cut out. And then we just fold up the sides. We fold up the sides where the square corners were. And if I had some tape, we'd have us a little box. Everybody see that? So what happens is we need to know what size square corners to cut out because we want our box to hold the maximum amount. And how much something holds is the volume of that box. Okay? So what we're doing in this class is coming up with the function, and then in calculus class you'll learn to take the derivative that will maximize your volume. All right, so let's see on paper how we might work this problem. Okay, so we had a rectangular piece of paper, and the dimensions were 8 by 15 inches. 8 inches, 15 inches. And then the next thing I did was come in and cut out square corners. And we don't know what size these little square corners are, so a nice little variable to use is x, little x by x square corners. So when I cut it out, now my piece of paper looked like this. Hopefully, something like this. Ooh, that turned out bad. Let's see here. Okay, something like this. Here's my piece of paper where I cut out, see, perfect match. Cut out the square corners. Okay, now this along here was originally 15 inches, but now I've whacked off a little X across here and a little X across here. So now what is the length of this side? 15 minus 2 X's, because I whacked off 2 X's there. And this part was 8 inches, but I whacked off a little X here and a little X here, so now this length is 8 minus 2X. All right, then the next thing we did was we folded along the dotted lines to make our box. Okay, so when you make your box, all right, this is probably going to look terrible. Good chance that it will. Actually, not as terrible as it could have been. Except it looks like my dimension, I got the box turned here, but we're going to pretend that's 15 minus 2x, so it sort of looks like it's matching up there. This is 8 minus 2x. And what became the height of my box when I folded it up? X, right? Because that was the part I'd cut off, and then when I fold it up, now that's where my height is going to be X. Does everybody see that? Height is X. That's the part here that I folded up. Is that good? Does that make sense? All right. So our particular problem was about finding volume of this box. So we want to express the volume of a box. And in general, the volume of a box is, the formula is, okay, or length times width times height, the volume of a box. Remember, that's the area of the bottom, length times width, times the height. Area of the bottom times the height. But we want to express our function volume in terms of x, where x is the little dimension here that was cut off. Little box x by x. Does anybody have a question for me at this point, or is that pretty clear? Okay. All right, I'm going to claim the length from our box is 15 minus 2x. The width of our box, 8 minus 2x. And the height of our box is x. So for this course, all you're doing is learning to write the volume function in terms of one variable, where x is the dimensions of the little square corner or the height. And in calculus, what you'll do is take a derivative to find out what values for x maximize the volume, and then when you plug back in here, substitute back in, that would give you the other dimensions. All right, anybody have a question for me on that problem?
So we go no further than right there, no solving it.
Right, this problem would have been find the function that defines the volume of the box in terms of x. Yep. Okay. If you multiply this out, this comes out to be a third degree. Times you multiply, you'll get an x cubed.
Mhm.
And in this class, we don't learn to find the maximum minimum values at x cubed. Not for x cubed. Everybody good? Okay, let's look at another problem off this sheet. This is another geometric solid, and this is problem number 5. And again, you have problems in your textbook that are similar, except it doesn't say find the least amount of material or the maximum volume or stuff like that, but just to really be sure that you're seeing all this. What dimensions of a cylindrical coffee can would require the least amount of metal? All right. If the can is to contain 64 cubic inches of coffee. Okay, so basically for this class, what we're going to do is we're going to set up a coffee can, which is a right circular cylinder, little can. We know our can is going to hold 64 cubic inches of coffee. That's a constraint equation. We want the can that holds 64 cubic inches. And our question is going to be, write the formula for least amount of material. That's the metal the can's made out of, right? The parts of the can. So that would be the surface area of the can. All right, so everybody got it? We've got a can. It can only hold 64 cubic inches. And we're going to write a function for surface area in terms of one variable. All right, so let me see if I can put some information up here. We've got a can. It says the can is to hold 64 cubic inches of coffee. And we're supposed to find the function for surface area, because that's the amount of material it takes to build your can. Okay, just like when you buy a soft drink can, it really does not minimize surface area because your can would be too wide, but they had to make a smaller can so it fits people's hand. So the drink company uses more metal than what it would really have to hold your soft drink if you got a canned soft drink, mostly because it'd be so short and fat you couldn't hold it in your hand. All right. Whoops. So we'll just call this R for radius, and we'll do height here. Okay, let's start out with some information here. We're told that the volume of this can is 64 cubic inches. And how do you find the volume of this solid? The area of the bottom, which is a circle, times the height, correct? So the volume is the area of the bottom, pi r squared, times height h. That's just area, pi r squared times the height. And we'll set that equal to 64. So this is really called our constraint equation. Because you have to be restricted on how much it's going to hold when you start talking about surface area. Otherwise, you're not looking for a particular can. You're not looking for a particular can. All right, now let's come up with the formula for surface area of our right circular cylinder. And let's use words first. When you have a can, your can's made of a bottom and a top, right? And both that bottom and top are circles, correct? So we have to get the area of the two circles, which are the bottom and the top. So our surface area, total surface area, is going to consist of the area of top and bottom. And then what else is your can made out of?
The outside.
Right, the part that goes around the outside. Here, I'm just going to take this little sheet right here. Yeah, this part right here of your can. Your can would have a bottom and a top, and then this part that goes around. So we'll just call it outside of the can. Outside can. That's the part that I just meant goes around. All right, so let's see if we can start getting a formula in here for surface area. Again, if you can verbalize in words what you're looking for, it looks pretty easy. All right, So the area of the bottom of my can is what? Pi r squared, and I got two of those. So we'll have 2 times pi r squared. Everybody see where the 2 came from? Pi r squared is the bottom, pi r squared is the top. 2 of those, 2 pi r squared. Okay, now a lot of people think around the outside of the can is difficult to figure out, but here's my great illustration and you'll never forget it. All right, we just want the area of this thing right here, right? So if I go around the outside, what is this thing called around the outside? Circumference. Do you know the formula for the circumference of a can? 2 pi r. Okay, now I'm going to take scissors and cut my can. When I open up that can that went around the outside, what is that? Just an old rectangle, right? What's this?
Length.
What's the formula for this side? 2 pi r, right? Because that's circumference of a circle. So that part's still 2 pi r even when you open it up. So if I want to get the area of this thing, this part is 2 pi r. And what was this? The height of my can, right? Height of my can. So the outside part of my can is
2 pi r plus
2
h.
pi r h, which is really just the area of this little rectangle where I took the can and cut it. Does that make sense? Now, isn't this fun? The answer to that is yes. I didn't hear everybody. Isn't this fun?
Oh, yeah.
I knew it was. All right. So our formula was to find the function, our question was to find the function for surface area. Well, when I look at what I have, I've got r's and h's in there. So I need to get it in terms of just one variable so that I'll have my function. All right, so does it look like to you that h would be the easy thing to replace because you got r's over here? So let's write our surface area only in terms of r. Our surface area will be a function of r, the radius. Okay, the first term's good, 2 pi r squared. And then we have 2 pi r. And now I need to find an expression for h that relates to my particular can that holds 64 cubic inches. Anybody have a good clue what to do here?
64 divided by I.
Yep. Go right here. H is 64 divided by pi r squared. And I just come where I have the h now and put in the 64 over pi r squared. Okay, and if you want to clean that up a little bit, that would be great. 2 pi r squared, and then 2 times 64 must be about 128. And it looks like the pi's will divide out. And we have 1 r in the numerator and 2 in the denominator, so it'll just leave us 1 r in the denominator. And so I have a formula now that will tell me the surface area of any can that holds 64 cubic inches based on whatever radius I choose. If you were running the business, you would be interested in minimizing the surface area, but this will give you the formula for finding the surface area of any can based on the radius only. Is that good? Questions? All right. The last little topic in this particular section is called demand equations. Demand equations. All right, so you've seen geometric figures, your rectangle, your little chicken pen. You've seen 2 solids. And now let's look at a demand equation. Demand. This is a very liberal arts business calculus related concept. So I'm just going to go directly to the calculus textbook if you happen to be taking 131. If you take 121, you still have these types of problems, you just have a different book. Okay, this is from the calculus book. The demand equation for a product is 2 minus 0.001x. Find the value of x, and the corresponding price P. So P is defined to be now the price of the item. So this demand equation really is like the consumer will demand or pay, depends on if it's the consumer or the store that's purchasing it. We can still call them a demand. Okay, basically, I guess what I would say is happening here, if you look at this equation, price is 2 minus 0.001x. X is going to represent the number of items that you purchase. X is the number of items that you purchase. So it looks like if you ordered a lot of items, your price is going to start to go down. So it's like buying in bulk. Buying in bulk, you've heard that if you buy 100 of something, they'll give you a little bit of a price break. Okay, that's what this is, the demand equation for a product. And we're supposed to, in this problem, maximize revenue. Okay, so revenue, remember we talked about cost, profit, and revenue. And P is the price, X is the number of items purchased, but we need a function for revenue. Okay, so let me just jot this down. Okay, we have a demand equation, and it's price equals 2 minus 0.001x. P is price, X is number of items, and we want to come up with the revenue function in terms of one variable. All right, remind me what revenue is. You're running a business, what's your revenue?
The money you took in for that day.
You are so good. The money you took in for that day. And the way you took in money was you sold so many items at a certain price. Okay, so price times number of items sold. Price times number of items sold is your revenue function. Yeah, I would beg for a lot of these on the test. So revenue then is going to be equal to, well, here's the formula for price because you're getting a little price break if you buy a bunch. So price is 2 minus 0.001x. And then how do you represent number of items sold? X. So revenue is price times X. That was a little bit too easy, wasn't it? All right, so you have some demand equations in your book, and part of that is reinforcing what is revenue, price times number of items sold. Okay? And that's where you quit. I've written the function only in terms of X. All right, you got lots of homework problems to have fun with. Again, geometric figures, those solids, and then your demand equation. Okay, all right, we're ready to go to the cumulative review. And we're going to look at even problems in our cumulative review because you got the odd problems answers in the back of the book. And we want to look at the papers that are turned in like we were grading them, because since I'm not collecting your homework and WebAssign is just taking your answers only, we need to look and see how you're expressing your work, and you guys tell me if you'd give full credit or if anything's missing. So this is a learning experience here. So we're on page 295 with the cumulative review. Okay. All right. And the first question I'm going to look at is off this sheet. And we're just looking at the even problems. This is number 2. Number 2 on page 295. And it says, find the real solutions of each equation. So in number 2, what kind of equation is this? What's the word?
Quadratic.
Quadratic. It's a quadratic equation. By the way, number 1 is called what kind of equation? Linear equation. Okay? Quadratic versus linear. Linear is to the first, quadratic is going to be to a second. All right, so to find the real solutions to this equation, the person's paper I'm looking at wrote down the problem, factored completely and perfectly, set each factor equal to 0. You have, can I write, I'm assuming y'all don't care if I write on your papers. You have a theorem somewhere earlier in your book that says if you have two numbers multiplied together to equal 0, and it can only equal 0 if, and it must be equal to 0, then A equals 0 or B equals 0. Okay? So completely multiplied, A times B equals 0, set each factor equal to 0, solve. These were linear factors. X is 4, X is 3. Oh, I meant to ask y'all, would y'all give full credit for this problem?
Yeah.
I
used the
certainly
quadratic.
would. And then the other little thing that you did, which was pretty nice, you went and double checked yourself to make sure you didn't make a mistake. That was a nice thing to do. It never hurts to go back and check in the original problem before you started playing around with it. That's a check plus, in case you're wondering. Excellent. Perfect. Questions, anybody?
I
Okay.
used the quadratic formula on that.
Okay, that would be absolutely okay. If you did the quadratic formula, x is negative b plus or minus square root b squared minus 4ac over 2a, where a is 1, b is negative 7, and c is 12, and you will get the very same answer.
thing.
So some people don't like to factor, and that's perfectly great. You just jump right on the quadratic formula and you're good. Thank you for bringing that up, and please speak up if you remember you did something differently, because we want to know about it. Everybody good on number 2? All right, let's look at number 4. Number 4, 4x squared plus 4x plus 1, again a quadratic equation. Now, I want you to compare the work of the previous example, number 2, to the next line in number 4. Somebody tell me something that's missing. What's missing on this line right here?
Equals to 0.
Equals 0. You got to make complete and accurate mathematical statements, because this line has to say equals the same thing as the next line. Okay, and the other thing is, if you didn't have the 0, you couldn't go say that's equal to 0 all of a sudden. One line's got, it's like in conversation, it's got to have a flow there that's correct. All right, so what happened here was that turned out to be a perfect square trinomial. Perfect square trinomial. And so it's called like a double root, and it factored, so x is equal to negative 1/2, and I think that's perfect. The only thing that I would have gotten a little excited for was that you didn't make a complete mathematical statement. Plus, I needed you to make a mistake here so that we can all learn, because somebody else. Okay, let's have true confessions. Who left off at equals 0? You didn't. I just looked at your paper. Oh, yes, you did. Oh, bad. Okay. All right, you did. Well, you did number 2 perfectly. All right, are we good on number 4?
And can we do number 5?
Number
That
5.
was kind of different.
Number 5, this person factored,
'Cause it
oh,
was unreal when I did it.
okay,
Yeah, I got no.
All right. I didn't get number 5 too.
okay. Number 5 is going to be, okay, let's do number 5.
Because when I got, when I got to the end, it was like square root of 60
Okay.
over 8 or something.
All right, let's go. I'm looking for a
negative
paper
60.
that has it. All right, let's go. I think that one's probably not right, is it? Yeah.
Well, it worked.
Actually, it doesn't. Doesn't. All right, let's go to this problem for number 5. And thank you for asking. 4x squared minus 2x plus 4 equals to 0. Now, you didn't see a way to factor it, although the other person did, but that was obviously not factored correctly. And here's your mistake. When you factor it out of 2, that number right there would have been a 4. Okay. All right, so if you can't see how to factor it, then you're going to go to the quadratic formula, and don't forget it's x equals. The quadratic formula is x equals this. You're finding x. Your a is 4, b is negative 2, I'm just double checking this, and c is equal to 4. So negative b is going to make that a positive 2. Plus or minus the square root of b squared, and it's the negative 2 whole thing that's squared to get the positive 4. Be careful with your parentheses, because if you just do minus 2 squared without parentheses, reality is it's only the 2 that's squared and then the minus. You meant the entire minus 2 squared. Minus 4 times 4 times 4 over 2 times 4. Okay, So then negative 2 squared is 4. 4 cubed is 64. And so x equals, and you got a negative 60 over 8. When you get a negative 60 under the radical, you're in the set of complex numbers. I is defined to be the square root of negative 1. And so at this point, you could write it as 2 plus or minus I square roots of 60 over 8. The problem is, in numbers, problems 1 through 8, it says real solutions. And when you get this negative underneath the radical, you're now under the set of complex numbers.
So you just write unreal?
Well, in the unreal, you write no real solutions.
Oh, okay.
No real. But on a test, I would have you solve of the set of all numbers, not just complex or real.
Because number 9 was the same thing as that, but you just had to put the I.
Yeah, because it asked for the complex number system. Thank you for asking that, yeah. This one, because it said under the set of real numbers, there's no real solution. Everybody good? Perfect. All right, let's look at number 6. Okay, we'll go back to this one. Number 6. You were asked to solve this. What kind of equation is this called? What's the word? Radical equation. And it happens to be a cube root. Cube root of 1 minus x equals 2. So to get rid of a cube root, you actually cube both sides.
1 minus x equals 8.
Okay, let's put in all the steps here. You got a cube root of 1 minus x equals 2x. And now when you cube both sides, the cube of a cube root will eliminate the radical, so you get 1 minus x equals 8, because 2 cubed is 8. So negative x is equal to, subtract 1 from both sides, I guess that would be now 7. So x is negative 7. Okay, is that number 6? X is negative 7. All right. Somehow when you cubed a 2, all of a sudden you got a square root. You kind of lost me on that. To get rid of a square root, you square both sides. To get rid of a cube root, you cube both sides.
Let's skip the step.
Skipped a step.
And what I thought there was squared on each side.
Okay. All right. Okay. Are you good now? All right. Important that it goes to long-term memories. All right. That was number 6. Let's go to number 8. Number 8. This is really nice here. Number 8. Number 8. Woo! Sorry about that.
Absolute value.
Staple that, put that back together. Number 8. What kind of equation is this called?
Absolute value.
Absolute value. And when you have the absolute value of A is equal to, say, 3, this is just an example. What values are A? What can you take the absolute value of that gives you 3?
3 and negative 3.
Okay, so A has to be 3 or A has to be minus 3. Okay, so if you have the absolute value of something equal to 1, then what's inside here has to be equal to 1 or minus 1. So we need a 2 minus 3x equals negative 1 also here. Okay, so you came down, you subtracted 2, so whoops, did we lose something? What's a negative divided by a negative here? Positive. It's negative 1 divided by negative 3. You were dividing both sides by negative 3. Negative over negative is positive. Okay, and then you also have 2 minus 3x equals negative 1. Minus 3x, subtract 2 from both sides. And when you divide both sides by negative 3, you get x equals positive 1. Okay? All right. So what we're expecting here is that there will be some mistakes because you were going back into chapter 1 and we want to all learn from those mistakes. Okay, how many knew to do 1 and negative 1? Raise your hand. All right, so that means you're among friends there. All right, absolute value. Send it to your long-term memory. We learned so much from mistakes.
Can you do number 9?
Number 9, yes. Let's just go to yours. Quadratic, ooh, can't see it, can you? Because I wrote all over it in red. Let me find another one.
I think my number 9 was.
I haven't either.
Someone did the,
Let's check this number 9. That one wasn't done.
it's on mine.
Number 9 was one of the few I did right.
Yeah, it's on.
All right, here's yours. Number 9. Actually, we just did number 9 back when I did number 5 because it's the very same problem. Number 9 was the same question except in number 9,
You have to
it-
solve it in terms of the complex number.
right, right. So if you'll go back and look at the way I just did number 5 earlier.
Just if my answer was right, because I wasn't sure how, if, no, not.
Oh, yeah. You're very, the I, the
That's
only
what I was
thing is
confused
you got to
on.
be careful the I's not under the square root.
Okay.
Let me just see if that kind of, okay, things are looking good to right here. And I see that you got the I under the radical. So normally you put the I in front of the square root sign. Okay, so be careful the I's not underneath. Okay, is that good?
Yes.
Everybody good? Thank you. All right, so now we're on, I'm totally lost. We're on number 10.
10.
Okay, we'll look right here
It's on
for
the second page.
second
I
page.
forgot it. I have to go back and do it.
Do number 10.
There it is.
There it is. Number 10. Number 10 says, as an inequality, negative 2 is less than 3x minus 5, less than 7. So you're trying to find all x that solve this inequality. So basically, you treated it just like you did an equation. You added 5 to all parts.
Didn't really show.
So when you add 5 to negative 2, what do you get?
Yeah, you get negative. Or 3.
Okay, so you're going to add 5, so I believe that would be 3 is less than 3x. And then you add 5 to 7, and you get 12.
I don't know what I did.
Okay, and then what's the next step, everybody?
You divide by 3.
Divide by 3. 1 is less than x, less than 4. All right, so it probably wouldn't hurt when you're doing this to spread out your work a little bit. And you might even come underneath and say, I'm going to add 5. Sometimes we get in trouble trying to do too much in your head. Showing all your steps never hurts. Okay? Everybody good? All right, the next one is number 12. Put that one right there. Number 12. Number 12 is to graph this equation. How do you know what this is going to be the graph of? What is it the graph of, everybody? Line is in the form y equals mx plus b. Okay, what's the b here?
12.
12.
It's already in slope intercept.
12. We got a little something missing here. The y-intercept is 12. The slope is 3.
3 over 1.
3 over 1. All right, let's see if I can pull another one real fast. Did you get it right, Robert?
I did.
No, I don't think I finished that one.
Mine's on the graph paper.
You got yours on the back?
It's on the graph paper. I'm pretty sure.
Show one amount I did right.
Okay. All right, let's see if we can pull this one. Can you see it? Here's the x-axis labeled. Very nice, very nice.
Let's see it.
And the y-intercept is 12, which he's got way up here. Can you see the coordinate system here? Okay, and what he chose to do, which I think is a very good idea, the slope is 3 over 1. He wrote it as minus 3 over negative 1, so he didn't run off the graph paper. So he started at 12 and he went down 3 over 1 in the left direction, down 3 in the negative direction 1. Or he could have started here and gone up 3 over 1, but he was trying to stay in the graph. Okay, so it crosses the x-axis down here at negative 4. So if you write your slope, negative 3 over negative 1, go down 3 over negative 1, down 3 over negative 1. Absolutely perfect. Very nice. Is everybody good? Okay, number, that was 12. Number 14. Let's see what that looks like. Number 14. All right, this really should have been kind of a shifting kind of deal. What basic formula does this look like?
Parabola.
Y equals x squared. And what does this minus 3 tell you you're going to do?
Goes down.
You're going to shift down, which is called vertically, 3. And what about this x plus 1?
Left one.
You're going to go left 1. Okay? So there was not a reason to plot all these points because this is a good transformation problem. So you take this graph, y equals x squared, which I'll just sort of do it in red here. We know looks like this. What's the key points on the parabola?
0, 0, negative 1.
Okay, good. 0, 0, 1, 1, negative 1, 1. We're going to take it down 3. So if we dropped it down 3, it's going to, I'm just going to visualize it right here and double check these. So 1, 2, 3, I'm going to drop it down 3, keeping those same points, and go over 1. So I'm just going to put in my little axes across here. Okay, so your vertex then, vertex of the parabola is at negative 1, negative 3. Okay, so that's the point, negative 1, negative 3. And if you come over 1 and up 1, you're on your y-intercept, which is 0, negative 2. And if you go over to the left 1 and up 1, just following those 3 key points around, you would be at negative 2, negative 2. And this particular graph, you've got a restricted domain by having those dots there. You need to extend past the restricted domain. Okay? All right, so that's one of your basic graphs. Vertically 3, horizontally 1 to the left. Okay? Everybody good? All right, number 16. Had to go back and use the distance formula. 16. The distance is equal to, you know where this came from, right? The distance formula. All it is, I'm going to just draw on this. You got 2 points, and you want to find the distance between them. Basically, all you're doing is setting up a little right triangle. And this is your changes in your x. This is your changes in your y. And your good old Pythagorean theorem. This, a squared plus b squared equals c squared. This is your distance along here, so it's the square root of a squared plus b squared. There's a plus in here. Somebody left that out. Very important. All right. Okay, so your distance squared is equal to delta x squared plus delta y squared, or your distance is the square root of the difference in the x's square, difference in the y square. Okay, it's just the Pythagorean theorem. All right, so for number 16, your 2 points were negative 1. Let me write those down. Negative 1, 3, and 4, negative 2. All right, so the distance is equal to the square root of the difference between the x's, negative 1 minus 4 squared, plus the difference between the y's, 3 minus a negative 2 squared. So negative 5 squared is 25, and 3 plus 2 is 5. 5 squared is 25. Square root of 50. Square root of 50 is fine for me. I don't know that it said you had to put it in decimal form, but square root of 50 is perfect. Be sure, though, that you're making accurate statements. There are a plus in there. Everybody good? Okay, number 18. Let's look at that. Number 18. Whoops. I'm about to mix everybody's papers up. Sorry about that. I'll find them. Number 18, you were asked to find the intercepts. Well, to find the x-intercept, you let y be 0. So 0 equals 3x squared plus 14x minus 5. And why did you all of a sudden put a -5 in there? To find the x-intercept, you can't all of a sudden go put -5. I think you did that from the y-intercept. The y-intercept, you let x be 0 and y is -5. Check. But to find the x-intercept, you have to say 0 equals 3x squared plus 14x minus 5. What kind of equation is this, everybody? Quadratic. And the first thing you try to do is factor. If you don't like to factor, you jump on the quadratic formula, right? Which is probably, I bet, what you did because you don't like to factor. This factors to 3x minus 1 and x plus 5. All right, you couldn't just all of a sudden go put in a -5. You know that had to be a 0 because that was a y-intercept. All right, so x is equal to 1/3 and x is equal to -5. All right, so this is the graph of a parabola. And you know it's going to open up because it has a positive in front of the x squared. It's going to touch the y-axis at -5, and it's going to intersect the x-axis at two places, -1/3 and -5. Positive 1/3 and -5. Any questions on 18? Yes. Excuse me?
When you're figuring out y equals to 0, I can't understand that.
You know,
This side.
this side? When you're looking for your x-intercept, it says where does it cross the x-axis? And every value on the x-axis has a y value 0. X-intercept means where's it touching the x-axis. So that's why you have to put in 0 for y and solve for x. Where does it touch the x-axis?
But that, what he's done or she's done is just that I should not look at that.
This part right here was just verifying that the y-intercept is -5, because if you put in -5 for x, it came out to be 0. So this part's not true. I mean, it's x equal -5 is not a true statement. Well, it did come out to be that by accident here, but that's not how you solve it. Did I answer?
Yeah.
Is everybody good?
So, x equals 1/3 and x equals -5.
Yes.
Okay.
Yes. Over here it's going to cross at -5, and here it's going to cross at 1/3. The y-intercept's down here at -5, and so your graph's going to go like this, if you were going to graph it somehow. Okay, we'll work on graphing quadratics a little better later, but that's it. Okay? Ooh, I graphed it in the wrong problem anyway. Sorry. All right, number 20. Let's go to number 20. Number 20 says, find the equation of the line perpendicular to a particular line passing through the point, put it in slope-intercept form. All right, what do you know about the slopes of perpendicular lines?
Straight up, vertical.
Negative.
There's one that.
Yeah, well, yeah, they make right angles. And if one slope is, say, 3, what's the other slope?
-1/3.
-1/3. The slopes are negative reciprocals. So you start out with the line you're given, and you want to find its slope. What is the slope of this line, y equals 2x plus 1? 2. This has slope 2. So the slope of a perpendicular line to that would have to be -1/2, negative reciprocals. All right, and then that line that's perpendicular is going to pass through the point 3, 5. An easy way to go is the point slope form, right? Y minus the y coordinate, y minus 5, equals the slope times x minus the x coordinate. Y minus 5 equals that slope times x minus the x coordinate. Remember, that's called point slope form. Okay, but of course the problem didn't ask for point slope, it asked for slope intercept. So really all I have to do is solve this for y, and it'll be in slope intercept. Y equals, and I'm going to multiply that out, -1/2 x plus 3/2. 1/2 times -1/2 times -3 is a +3/2. And then I'm going to add 5 to that. So y equals negative 1/2 x plus 13 halves plus 13 halves. Is that good? All right, so this is the equation of a line that's going to hit this one and be perpendicular to it. Is everybody good? All right, so then the problem says graph both lines. Let's see if we have somebody who has it graphed. Y'all do? Okay, let me see if it's in this problem. Oops, that one doesn't. All right,
Oh my God.
this one right here? Okay. All right. The first graph is, here's the x and y axis in case this is a little faint. That's all right. You can pretty much see it. Y equals 2x plus 1. The y-intercept is 1. Here's the 1. And you went up 2 over 1. So here's the graph of that line, which I'm going to sketch over in blue. So you just go up 2 over 1, up 2 over 1. Very nice graph. All right, and then the graph of y equals negative 1/2 x plus 13 halves. 13 halves is about 6.5. 1, 2, 3, 4, 5, 6. So that's 13 halves right there. And did you try to come down 1 and over 2 from that? So you came to the halfway mark and then came over 2. That looks about right. Come to the halfway mark and come over 2 units. Okay, or you could have just found x and y intercepts and sketched it through, or found a couple other points and you would have been fine. These two
started from 3.5 and made it easy.
Okay, so you found a point that was,
I gave you the point.
oh, it gave you the 0.35. Okay, you're right. Gave you the 0.35, so you went down 1 over 2, down 1 over 2. Absolutely perfect. Everybody good? So those two lines come in at right angles. All right, let's go to problem number 22. Let's see what we got here. Everybody doing okay? Okay. Number 22. 22, where is it? Oh, there's a lot to 22, isn't there? Okay, 22. I'll check the answers as I go against the key here, and then I'll know. All right, you're given the function f of x equals x squared minus 4x plus 1. Evaluate f at 2, just means you're putting in a 2 where the x is, plug and chug, and negative 3 is perfect. All right, stop me if you have a question about it. F of x plus f of 2, it just means write down f of x, and then put in the f of 2 that you found from b, add the 1 and the negative 3, and your answer is x squared minus 4x minus 2, and that is perfect. Any questions on that? Okay, C says find f of negative x. That means that where you have an x in the original problem, all right,
You just
I'm sorry.
go ahead.
Just distribute an X throughout the whole thing?
Right. No,
Oh.
no, that's if the negative's on the outside. All right, let's come back. It's wherever you have an x, you're just going to use some parentheses here and put a 1. All right, so if you're looking at f of negative x, the little negative x has got to go in here. Now, what happens when you square negative x?
Get a positive.
Get a positive x. So you want to be careful when to use parentheses and when not to use parentheses. You're replacing the whole thing with the x. So it's going to be positive x squared, and then negative times a negative is a positive. So if we just make that a little plus right there, we would be okay. Everybody good? Appreciate that whoever did this, you're showing me every little step, because then we learn. Okay, D is where you have the minus on the outside of the f of x.
I knew I did it.
Some way or another.
Yeah.
So now this is like saying negative 1 times
The whole thing.
f of x. So you're going to multiply through by a negative, and that switches all your signs, and that is perfect. Correct?
Yes.
Okay. All right, E is f of x plus 2. So again, if you would write your problem like the parentheses square minus 4 times the parentheses plus 1, if you're looking at f of x plus 2, the x plus 2 goes in. I'm looking down here, minus 4 times x plus 2. Whoops, there's a plus 1 right here. Plus 1. Plus 1. All right, so when you square that, you get x squared plus 4x plus 4. That part's right. Careful to distribute the negatives. You did. Negative 4x minus 8, and then there's a plus 1 right here. X squared, and the 4x minus 4x must have canceled out. And 4 minus 8 is negative 4 plus, that's a plus 1. Somehow you looked out with the same right answer at the end anyway. X squared minus 3. It was 4 minus 8 is negative 4 plus 1 is negative 3. Okay? Everybody good? And the last, how many minutes do I have? 1 minute? Okay. At the beginning of the lecture next, whatever it is, we're going to pick up with F and then do 24 and then move on into the next topic. All right? Thanks. That again. Alrighty. Now can I repeat the same thing I just said? Are we ready? All right, welcome back. We're now continuing on with lecture 5B, and in 5A we constructed some functions using geometry, some solids, and a demand equation. And the comment was made, well, you use problems out of the calculus book. Well, I did that only to motivate the topic. I now have your textbook in front of me. And just wanted to point out in your exercises in page 283, there's your demand equation, and you have to come up with the revenue function. So that was one of those things we did. Down at the bottom of page 283, you've got a rectangular field with some fencing, and you have to come up with a formula for the area of that. Notice number 8 is very similar to the calculus problem. You have one side of the field lies along a river. I think we had a barn with our chickens, okay, but you still got to come up with your area. And at the bottom of page 282, here's your setting up your formulas for your volume of your cylinder, and then it talks to you about a volume of a cone, but it gives you the formula there. You don't have to memorize the volume of a cone, but you do want the cylinder and the box, okay? And then once we get into section 3.1, you're going to see more of those box problems where you're building a box like what we were doing in the calculus. Okay, so thank you for mentioning that to me. All right, so what we're going to do is continue on with our cumulative review, and then we'll move into chapter 3. And we're on page 295, and at where we had to stop last time, let me find my page again. We were working on number 22. We were working on number 22. We did not finish 22. Okay, we were at section F. Let's see, did we do E? Don't remember doing E. Yeah, we did E. Okay, we ended up working with E, f of x plus 2. Just remember, in the original function where there's an x, put parentheses, and then in this case replace it with the x plus 2. You squared the x plus 2, you multiplied negative 4 times the x plus 2, and then there was a plus 1 there. So that came out to be x squared minus 3. X squared minus 3. Okay, now problem F, you were asked to find f of x plus h minus f of x over h. Somebody remind me what this is the formula for. What's it called?
Difference question.
Okay, that's called the difference. Oops, my pen messed up. Difference quotient. And who remembers what this gives you the slope of? Secant line. Okay, remember giving 2 points on a curve and drawing the line through that curve? And so that would give you the slope between any 2 points on the curve. All right, so it's just like you have f of x plus h. We've got to be careful. F of x plus h, we never found that. See, f of anything is anything squared minus 4 times that anything plus 1. So if you're looking for f of x plus h, don't you go in here and put a little x plus h inside the parentheses? And look what this person did. They did f of x and then plus h. That is saying this is not equal to f of x and then a plus h, which is what you did. There's f of x and then plus h. It's f of the quantity x plus h. So we want to be careful and square the x plus h. X squared plus 2xh plus h squared. And then negative 4 times the x plus h is minus 4x minus 4h, and then plus 1. Is there a question on that? This is a mistake that happens a lot, and it's f of the quantity x plus h. It's not f of x and then a plus h. Do you see the difference? See the difference? All right. So the problem asks for f of x plus h minus the original function divided by h. So if we come down and copy what our f of x plus h is, we have x squared plus 2xh plus h squared minus 4x minus 4h plus 1. And then you're going to subtract your f of x. F of x is x squared minus 4x plus 1. And all this is over h. Somebody get this right?
I think I did. I'm pretty sure I did.
Okay.
Dang.
All right, here's one. Let's double check that. X squared 2xh plus h squared minus 4x minus 4h plus 1 minus, and notice how nice these parentheses are, because you want to be able to block it off, the f of x plus h minus the f of x. That is very good, over the h. And then the next thing this person noticed was that x squared minus x squared canceled out, negative 4x plus, don't forget your negatives got to be distributed all through here, plus 4x, and then positive 1 and the minus 1 canceled out. So you were left with 2xh, the h squared, and the minus 4h. And from this step to this step, somebody tell me what they did. What happened from this step to the final answer here?
Times h.
Okay, did a factoring. Factoring, so you factored h out of the numerator, 2x plus h minus 4. And when everything is completely factored and you've got the multiplication, the h's will divide out. Okay, and this person knew that they were basically factoring out a h and did that division there. But basically, this is showing the factoring. Okay, everybody good? Questions? All right, again, this paper, the original paper I looked at, made a common mistake that really hurts on a test. You always have one of these questions on a test and the final exam because it's very calculus related. It is important to note that f of x plus h is not f of x and then a plus h. If you do those little open parentheses, you'll get it. All right, any questions on that before I move on? All right, let's go to problem number 24. Determine where the following graph, oh, well, hey, was that one easy or what? Is this a function? How do you know looking at it?
Vertical line test.
Passes the vertical line test. Remember, for a function, for each x, you only have one choice for y, and that's why the vertical line test works. Okay? All right, you have the answers to the odd in the back of the book. If you have questions about it, for you guys in here, you can, show me your work. And if you're doing this by video or distance ed, you can always post it in Vista and get some help with that. All righty, we are now experts and reviewed. And I thank all of you for doing this work so that I could use it on screen. That was a great help. All right, we are ready to move into Chapter 3, Section 1. Chapter 3, Section 1. And let's look, oops, I don't know why I closed the book. And let's look at the objectives that you're responsible for in Chapter 3, Section 1. We're on page, where is the page?
298.
Thank you. Page 298. All right, if you look at the sheet that I gave you that indicated the sections, you're going to have objective 2, 3, and 4. Now you're going to go, well, why are you skipping objective 1, which is graph a quadratic function using transformations? We really haven't skipped objective 1. We did objective 1 when we were doing our transformations. This particular section of the textbook for the objective is requiring that you use the method of completing the square to get it to that form. And we're not going to require the method of completing the square to get it to that form. So yes, we do have to know how to graph using transformations, and that will be our problem we start out with. But we're not going to have to complete the square. Okay? All right, so we want to be able, given the graph of a quadratic or given the equation, be able to identify the vertex. Go ahead and impress me. Where do you find the vertex of the parabola? If the parabola is opening up, it's your very lowest point, and if your parabola is opening down, the vertex is the very highest point. Tell me about an axis of symmetry. Why do you even talk about an axis of symmetry for a parabola? Anybody know about the axis of symmetry?
And if you put a line,
They have to
if you fold it in half.
Yes, the axis of symmetry would be the vertical line that goes right through the vertex, because you could fold on that and the parabola would just fit right on top of itself. It's symmetric about its axis of symmetry. That's why we've been able to go over 1, up 1, this way, over 1, up 1, go over 2, up 4, go over this way, 2 and up 4. It's symmetric about the vertical line that passes right through the vertex. Okay, and then number 4, we want to use the maximum or minimum values of a quadratic to solve applied problems. We're going to go back to our little chicken pen problem that we did earlier, and we're going to find the maximum value. Because if we have a quadratic, if you have a parabola that opens up, a quadratic function, your max or min is going to occur at the vertex. So we'll be able to go a step further on that. All right, so again, we're skipping number 1 in the book per se because it's requiring completing the square, but we want to be able to do transformation. So I have a problem for us to start out with. Okay, so we want to review just a second. Transformations. And my problem is going to be y equals 2 times x plus 3 squared minus 4. And we want to sketch the graph of this function. So let's try to mark off the unit somewhat good. Graph paper would have been nice. Thank you. I'll probably use you after this. All right. Reviewing transformations. What's my basic function? That's a too easy question, isn't it? Y equals x squared. Okay, my basic function is y equals x squared. What is this 2 right here going to do? What kind of stretch? What's the word? Vertical stretch. So then we're going to do a vertical stretch by a factor of 2. The y values are being multiplied by 2, so we have y equals 2x squared. And then what does this little minus 4 right here that tell us we're going to do?
Shift down 4.
Okay, we're going to do vertical shift, which is down 4. And then the little x plus 3 tells us we're going to go,
To the left.
okay, a horizontal shift this way of 3. Okay? All right, so we've analyzed it, and we're going to know how to graph it. All right, so let's start out with y equals x squared, 0, 0, 1, 1. Ooh, I didn't keep my units the same, did I? That is bad. I'm going to do your paper. So sure. I'm just going to start over because I made a bad thing. Here's x and y. 1, 2, 3, 4. It's amazing how much better graph paper is, isn't it? Okay, negative 4. 1, 2, 3, 4. Oops.
And you had graph paper too.
I know, I had graph paper and still blew it. All right, so the first thing we're going to do is graph y equals x squared, 0, 0, 1, 1, negative 1, negative 1. And the graph looks like this. Keep up with those key points. Okay. All right. Y equals 2x squared. It says I'm taking my old y, and my old y values are multiplied by 2. So we're going to multiply these old y values by 2. So 0 times 2 is still 0. And now we have 1 times 2. So now we have 1 times 2. And then 1 times 2 over here. So our points are negative 1, 2, 1, and 2. So the red now is a vertical stretch. This is y equals 2x squared. Okay, would have been a little easier to see also if I'd done 2, 4, because now it'd be 2, 8 vertical stretch. Okay, now we're going to shift it down 4, and that's a vertical, so we're going to just take all those little y values and take 4 off of it, correct? So if I subtract 4 off the 2, I'm now going to have the point, what, 1, negative 2? 1, negative 2. I'm just pulling 4 off those y values because it says a vertical shift down of 4. 0 subtract 4, so now I have 0, negative 4. And subtract 4 from that 2, and we have negative 1, negative 2, right there. Okay, so there's my shift down. So far we have y equals 2x squared minus 4.
Did you do that from the original?
No, I'm doing it from the 2x squared. Subtract 4 from the 2. I did the vertical, and now I'm pulling the 2x squared, and then I'm pulling 4 off the y values for the 2x squared. Okay, and now we're going to go horizontal 3. If you're going horizontal, which ones are you playing with? X or Y values? X values. So we're going this way 3, so I'm going to pull 3 off each of these. So negative 1 minus 3 is going to make that a negative 4. So this comes over to right here. So that's negative 4, negative 2. We'll come this way 3. So we were at negative 1 and I'm coming over. We're going to subtract 3 from the 0, and that's going to bring that over here to negative 3, negative 4. And we're going to subtract 3 from the 1, and that's going to bring it over here at negative 2. So this now is subtracting 3 from that. We have negative 2, negative 2. And all I've done is basically picked up this parabola and moved it to the left. Moved it this way 3 units. So here's the graph that we were looking for. Y equals 2 times x plus 3 squared minus 4. Right there. Everybody got it? Got the transformations? All right. Now the reason, again, we skipped section 1 in this exercise was it was saying, well, suppose it's not already in this form. How do you complete the square to get that? Well, we're going to go with a second option for graphing because it's generally a little bit quicker to do if it's a quadratic. All right, and I'm on page 305 in the book, page 305. Thanks for the graph paper. This is page 305 in your textbook, and we're going to look for the steps for graphing a quadratic function by hand, and we're going to go with option 2. And option 2 says, let's go find the vertex, determine your vertex, and we always will look for y-intercept. And actually, step 4 is to ask you, really, are you going to have any x-intercepts? You can go right away to solving the x-intercept by letting y equal to 0, and so you've got a quadratic, and you just found out you either factor or use quadratic formula, and if you get a negative underneath the radical, you got complex solutions, which means no real numbers. And then plot a few points, and you got it made. Okay? So we're going to go with option 2 on page 305. And I want to flip over to page 301, right above objective number 2, page 301. And on page 301, it says in almost every case, it is easier to obtain the vertex of the quadratic formula by memorizing this formula. Well, your question really becomes, well, where did that formula come from? Did it just fall out of the sky? Well, if you look at the top of page 301, this is where they were completing the square to get it in the form for your transformations. They were completing the square. And so when you have a times x minus h, when they completed the square, that h is going to have to be the negative b over 2a. So I just wanted you to know that you don't just take everything at face value. There really was a place where this formula was derived, and it shows it here in the book. Basically, I'm just asking you to memorize it. I just wanted you to know it didn't fall out of the sky. All right. So what we're going to do is we're going to take the problem that we just did, y equals 2 times x plus 3 squared minus 4, and we're going to pretend that we don't know how to do it with transformations. And the way I'm going to do that is I'm going to expand the product here so it doesn't look like the transformation. So I'm going to square the x plus 3, and I get x squared plus 6x plus 9. Then we have the minus 4. So that's 2x squared plus 12x plus 18 minus 4, which is equal to 2x squared plus 12x plus 14. All right, so this is really where we're starting. We're actually graphing what we just graphed, but we're going to pretend that we don't know it in the form for the transformations, just so you can see it using these steps. All right, so we talked about the little steps on page, I already lost the page, 308, 305. But let's take it, we want to sketch the graph. And I have a few little steps I like to put in first. I like to know, is this graph going to open up or down? Is it going to open up or is it going to open down? And what would everybody say? Up. And why is it up?
A is positive.
The A is positive. She's saying if you have y equals ax squared plus bx plus c, if the A is greater than 0, it's going to open up. If the A is less than 0, it's going to open downward. Okay? So it's going to open up because you got a positive 2 there. All right, a second thing is to look for the y-intercept. It's always helpful to know a point on the curve. The y-intercept is always the easy one. Just looking at this, what is your y-intercept, everybody? 14. Remember, y-intercept, you let x equal 0. So if you let x equal to 0, the y is going to be equal to 14. Okay? And I'm going to start sketching this again based on the information I get, and then we'll compare it to the other one I just did, which I've already stuck somewhere, but I'll find it. All right, so actually I think I'll turn it this way, so I have a lot of space. This is the x-axis. Here's the y-axis. And we're going to do by 2's here. 2, 4, 6, 8, 10, 12, 14. All right, so there's the y-intercept. And we'll do the x-axis by 1 so I can see it. -1, 2. Okay, so my x-axis and the units on the x-axis and the y-axis can be different. Okay, so it's by 2's along the y-axis and it's by 1's along the x-axis. All right, so we got the y-intercept as oh, I put it in the wrong place. It's positive 14. Ooh, 2, 4, 6, come on, 8, 10, 12, 14. You were hoping it wasn't going to work. I could already tell. Okay, there it is. 14 is the y-intercept. Okay? All right, now how do you find the x-intercepts?
Y equals 0.
Okay, your y is equal to 0. So we have 0 equals 2x squared plus 12x plus 14. All right, and that's not going to be something that easily factors, I don't believe. You can factor out a 2, but I don't think it's going to factor after that. So let's go into the quadratic formula. X equals negative b, which is negative 12, plus or minus, I don't think so. Try working it out. Try it, and then tell me. B squared minus 4 times 2 times 14 over 2a, which is 4. Is that correct? Okay. We have to go to the next page. So x is equal to negative 12 plus or minus the square root of 144. And 4 times 2 is 8, and 8 times 14, somebody double check me, but I think that's 112. Is that correct? Oh, I got a calculator. Yeah, okay, good. All right, so we get negative 12 plus or minus the square root of, and 144 minus 112 is 32 over 4. All right, so x then is negative 12 plus the square root of 32 over 4, and negative 12 minus the square root of 32 over 4. And let's put that in the calculator. Square root of 32 minus 12, all that divided by 4 gives me a negative 1.59 approximately. And minus 12 minus the square root of 32, all that divided by 4 is approximately a negative 4.41. Okay? All right, so we do have real solutions. They're just not pretty, not nice, even numbers. All right, and these are approximations because the square root of 32 is a irrational number. All right, so now let's go back. Everybody good on this? Let's go back to our graph, and we're going to plot about a negative 4.41. 1, 2, 3, 4. If you make your dot big enough, you're bound to hit it. This is about negative 4.41. And about negative 1.59 is somewhere right in here. Negative 1.59 is somewhere right there. Okay? So now I have my y-intercept and I have my x-intercepts. Okay? All right, and we already know the parabola is going to open up. Now let's go number 3 part. Okay, so 1 was up or down, 2 is the x and y intercepts. Again, if you got a negative underneath the radical, you would know it's not going to touch the x-axis because that's the real numbers. All right, and then the third thing, let's do the vertex. And you want to memorize that x is negative b over 2a is your formula. Negative b over 2a. B is 12, so that's negative 12 over 2, and the a is 2. So negative 12 over 4 is negative 3. And by the way, we already knew that when we did our transformations, that the x-coordinate of the vertex was negative 3. Okay, but using this little formula. How do you now find the y-coordinate of the vertex? If you know x is negative 3, how do you find the y value?
Put it into the f of x.
Plug it into your formula. So you have 2 times negative 3 squared plus 12 times negative 3 plus 14. Your problem was 2x squared plus 12x plus 14. That would give us 2 times 9. 12 times negative 3 is negative 36 plus 14. 9 times 2 is 18. So 18 minus 36 plus 14 gives me negative 4. And of course that's where we had our vertex on this problem, negative 3, negative 4. But using our formula, we just found it's negative 3, negative 4. Does anybody have a question on finding the vertex? Okay, so we'll come down here and plot negative 3. That would be here. Negative 3, 1, 2, 3. Negative 4 is right here. Okay, I don't have the same units on my graph this time, I don't guess. And the parabola looks like this. And we actually know that it's going to have a y-intercept here of 14. All right. The axis of symmetry is the vertical line that goes right through the vertex. All right, this is the point, as you know, negative 3, negative 4. That's the vertex. Somebody tell me right away what's the equation of this vertical line.
Opposite of b over 2.
What's the equation of this line?
Opposite of b over 2a.
Okay, x is equal to negative b over 2a, but it's going right through the point negative 3, 4, so what's the equation for it?
X equals.
Oh, yeah.
X
X equals
equals
negative
-3, right? That's your axis of symmetry. Goes right through the vertex. Axis of symmetry. Okay. Now, I want another point on this graph, and I'm at x equals -3. And if I go to the right 3 units, the y value is 14. Somebody tell me what the other point is that's going to have a y value 14. To the right 3, the y value is 14. So what do I need to do?
Left.
Left 3, and the y value will be 14 also. So 3 over, that would be at -3, -4, -5, -6. So at -6, the y value is also 14.
Can you do that again?
I will. Thank you for asking. Okay. The axis of symmetry is a line that goes right through the vertex, which means that if you fold your paper along the axis of symmetry, the parabola fits on top of itself. Okay. So if you're at the axis of symmetry and you go 3 units to the right and you have a y value that you already know is 14, then you should be able to go 3 units to the left and the y value would also be 14. And also, you know other things. You go over 1, up 1, you got a point. Go to the left 1, up 1, you also got another point. Okay, is that good, everybody? All right. You told me that this opens up so it has a minimum value. What is the minimum value of the function? If I say, what's the minimum value, everybody would say,
-3.
-4.
-3.
okay, value of the function means a y value, remember? Value of the function means y value, f of x. Okay, so the minimum value of this function is -4. The minimum value.
What is -3?
-3 is the x coordinate where the minimum value occurs.
What about like the maximum and the
There's
minimum?
okay, this curve's going to go like this forever and ever and ever. Does it have
I
a
mean
max?
The minimum. Or
Okay,
whatever you call it.
right. The minimum point is -3, -4. But when a question says, well, what is the minimum value of the function? You're saying, what is the value of the function at -3? The function is like y equals, so minimum value of the function, the minimum y value. Okay, so the minimum value of the function here is -4. Got it? Good. Okay, what is the range for this function? Range. I'm just reviewing you from other stuff. What's the range?
Positive infinity. Or, wait,
What's this?
the range is the y's, right?
Right. So what's the range?
Well, it's going to keep going up, right?
So
I'm
it's
confused.
from,
-4 to 14.
okay, the curve goes forever and ever and ever
Infinity.
to infinity.
Uh,
What's your domain?
-6 to infinity.
The curve keeps going forever and ever. Domain is x values. What is it?
Negative infinity.
Yeah, negative infinity to infinity. You can put in any value for x you want,
Thought it
and you'll get a y value, but the range is what is the y values.
Okay.
Got it? Where does this function increase?
From
Where is it increasing? Over what open interval is it increasing?
-3 to
Infinity
0.
Yeah. -3 where?
to infinity.
To infinity. You're saying over what values of x is the y values getting bigger. So once you start at -3 and keep going this way, the curve just gets bigger and bigger and bigger, right? Okay, where is it decreasing? Over what interval?
Negative infinity to -4.
Whoops,
Or
-3.
-3.
Yep, decreasing.
For the increase, why would you say -4? Like on the y value, you have to look at the x value.
Yes, when it's asking you over what intervals is it increasing, it means over what domain.
Okay.
Over what domain is it increasing and decreasing. Okay? Everybody good? All right. Any questions on this? All right, we're going to apply this to some applications, which are very important. And we're going to go back to our little chicken problem from the other day. And we're going to actually answer this question that's on this sheet. All right, so we're going to look at some of our applications for quadratics. All right, this was the problem where you had the rancher that had 100 feet of chicken wire to make the chicken yard, and one side was against the barn where no wire was needed. And our question is going to be, what dimensions maximize the area? We're going to go through this again, even though we did it a couple lectures ago, but we are going to, excuse me? Okay, remember, all your little comments are being picked up. Not always, and they are disruptive to people listening to the tape. Okay. All right. We'll go back and set this up, but this time we are actually going to go ahead and maximize what that area is. And you have these kinds of problems in your textbook. For example, on page 307, example 9, maximizing the area enclosed by a fence, just like this calculus-related problem. And you will have plenty of homework problems that have to do with areas. I'm on page 314 in your book, enclosing a rectangular field, and there's a field next to a river. Okay? So, very similar to what's in your textbook. All right, but this is one that's actually in calculus. All right, so let's just go back and remember how to do this problem. Remember you had your barn? This was your barn. You're going to put your little fence around, put your chickens in. Remember this problem? And you had a length and a width. And you said you only had 100 feet of fencing to go all around this rectangle. What was your constraint equation here? What was your equation that added up to 100?
L into 2W.
Yes, L plus 2W. All right, that was your constraint, that you were only allowed to use 100 feet of fencing. Okay, but you want to focus on what you need the formula for that you need to maximize, and you want to maximize area. So we need to write the function for area, and you hope that's going to come out to be a quadratic, which is the section we're studying. All right, so we need the function area. And in general, the area of this rectangle is length times width. But we need to get this in terms of one variable. So remember, you come up here and use your constraint. L is equal to 100 minus 2W. 100 minus 2W. So area then, and in the place of L, I have 100 minus 2W times W. So I've written the area now as a function of the width. When I multiply this out, I get 100W minus 4W squared is my function. My area is a function of the width. And you might prefer to rewrite it in descending powers, 4W squared plus 100.
Well, where did the 4W come from?
Oh, well, that's a good
be 2W,
question.
right?
Should be a 2. 2. Sorry about that. Right here. 100, I was just seeing if you're paying attention. 100 minus 2W squared. Thank you. Thank you so very much. Okay? All right. Now, when you look at this, this almost looks something like y equals minus 2x squared plus, there's a W there. $100x. I mean, that looks similar to that if you're looking at it. Aaron, will you please stop doing that? All right. What's this the graph of, everybody, as soon as you see it? Parabola, is it open, up, or down?
Down.
Down. So the graph's going to go like this, And you know that wherever that vertex is, you're going to have a maximum value. All right, well, our problem's in terms of areas and W's. So if we were graphing this, along the x-axis, you're going to have W. And along the y-axis, you'll have area, correct? Because this area is a function of the W. So once we graph this thing, we will know what width gives the maximum area. All right. How do I find the x-coordinate of the vertex? And in our case, it'll be a w-coordinate. W. What's my little formula you just quickly memorized? For negative b over 2a. All right, because it's a w instead of an x, but it's still the same thing. My independent variable is w. All right, negative b is negative 100 over negative 2 times a, 2 times a. A is negative 2. I reverse those.
It wouldn't be a negative 2.
It's 2 times negative 2. I switched those signs by accident there. Okay, so we have negative 100 over negative 4, which is equal to 25. Okay?
Why is it not a negative 2 on the inside?
Negative 100, 2 times negative 2. I just did my commutative property and did them backwards and confused everybody. 2 times a is negative 2. It is negative 2 there. So this means where W is equal to 25, I'm going to have a maximum value here. All right, but the question asks for what are the dimensions? Okay, and then what is the maximum area? So if we know width is 25, how do I determine what the length is?
Plug it in.
So width
Plug and
is
check.
25. The length will be equal to 100 minus 2 times 25, or 100 minus 50, or 50. So the dimensions of my rectangle are going to be a 25 by 50. And notice that if I say 25 plus 50 plus 25, that's equal to my 100 feet of fencing that I started out with. Okay? All right, and then the question says, that's all this question asks. It said, what are the dimensions of this rectangle that will have the maximum area? And it said 25 by 50. 25 by 50 is the answer, and we found it. If you wanted to know, well, what is the maximum area, what would you do?
You would L into W.
Okay, you'd say length times width, 50 times
25.
times 25, and that would give you the
1250.
1250? Okay, good. So the actual area is 50 times 25, 1250 square units. And I guess that's feet, so square feet. Okay, everybody good? All right, let's work a problem right out of the book. Page 315, and we're looking at problem number 86. Okay, this is page 315, number 86. All right, I'll put it right here. All right, this is kind of popular type window these days. I actually think these are called Palladium windows now. But anyway, this calls it a Norman window, putting them in a house. A Norman window, this is number 86 on page 315. A Norman window has the shape of a rectangle surmounted by a semicircle of diameter equal to the width of the rectangle. Here's my picture. And they're going to tell me that the perimeter of this window is 20 feet. All the way around the outside is 20 feet. And we want to know what are the dimensions that will admit the most light in our window. So what the dimensions need to be so the most light comes in. And that just means we're maximizing the area of our window. All right, so we know that the perimeter all around the outside is 20. That's a restriction. We only want a perimeter of 20, and we want as much light as possible, means we're going to maximize the area. Everybody got it, the story? Okay, let's see if what we can come up with. All right, we're going to do a little quick drawing here. A rectangle, and then we have a semicircle on top. Okay, and the perimeter here is equal to 20 feet. Okay, and I'm just going to divide this up into two parts. We have a rectangle, and then we have a semicircle. Okay? All right, so the 20 feet is going to consist of the three parts of the rectangle. Let's give it a name. We'll call this length, and we'll call this width. Okay? So around these three parts, what's the equation? Length plus 2w, right? So we got a length plus 2w. W plus L plus another W. All right. And then we have to add to that this half a circle. Okay. So we're thinking about a circumference of a circle, correct?
Add 2 pi r.
Okay, a circumference of a circle is 2 pi r, but we only have a half of a circle. So we'll take 1/2 of the circumference. Everybody good so far? Yes.
Is the circle, or is that included with the perimeter being
Yes.
20 feet?
Yes. The all around the outside here has got to be 20. Isn't that what it says? If the perimeter of the window is 20, so all around the whole outside. Thanks for asking, because I might have misread it. All right. Now, do we know what R is with respect to L's and W's?
Half the length.
Okay. This is the radius. The radius is going to be half the length. So we have 1/2 the circumference is 1/2 times 2 is 1. So we got pi, and the radius is 1/2 L. I just divided out the 2's right here. Okay, is that good, everybody? So the perimeter around that half a circle there is pi times L over 2. Everybody got it? All right. And that is going to be equal to 20. All right, this is my constraint. And it's my constraint because I can only use 20 feet of fencing around this. Okay? All right, now, what is it that I'm really trying to maximize according to the problem? Area of this thing. All right, so I've got an area of a rectangle plus the area of 1/2 circle. Remember, if we put it in words first, that will help us out. We got the area of a rectangle plus the area of a half circle. So area equals, okay, what's the area of my rectangle? Length times width. And then this is going to be area of a rectangle and area of a half a circle. All right, what's the area for circle?
Pi r squared.
Pi r squared. Area of a circle is pi r squared?
Yeah.
Good. All right, but R really is what? 1/2 L? Okay, so area is LW plus 1/2 pi, and in the place of R, I'm going to use 1/2 L. And don't forget, the whole 1/2 L is squared, right? It's R squared. So that's length times width plus 1/2 pi. 1/2 L squared is 1/4 L squared. 1/2 L squared is 1/4 L squared without the parentheses. 1/2 squared is 1/4. All right, so final cleanup before we make some substitutions. We have LW, a half times a fourth is an eighth, 1/8 pi L squared. Okay? All right, now my areas in terms of two variables here. So we want to come up here and see which one's going to be the easiest one to figure out, and also looking at our equation. What should I solve up here for? The L or the W? I believe I would solve for the W, so I could put it right here. So we're going to solve this for W. So we have 20, I'm solving for the W, minus L minus pi over 2L equals 2W. All right, I've subtracted the L from both sides, and I subtracted the pi L over 2 from both sides. And then I've got to solve for W, which means I'm going to multiply through by a half, just solving the equation. Multiply through by a half, both sides of the equation. So that will give me 10 minus L over 2 minus pi over 4L. Just multiply through by a half. Okay? Everybody with me and okay? All right, so area then equals L, and in the place of W, I'm going to put 10 minus L over 2 minus pi over 4L, that's the W, plus 1/8 pi L squared. If you do it step by step, you're not going to make mistakes, I hope. Everybody with me? Now let's clean this up a little bit. I need to go to the next page. You got it? Actually, if I had a sheet of paper, I could continue here. Here's a blue sheet. I'll just pull this up so we can keep going. All right, so area then is equal to 10L minus L squared over 2 minus pi over 4L squared plus 1/8 pi L squared. Okay? Now this is looking a little bit bad, but you get a common denominator right here. You got a 4 and an 8, and you've also got an L squared there. So what's going to end up happening most likely in this particular problem is you're just going to get a very good approximation, because you're going to change pi to something like 3.14. But what I'm most concerned with is that you can set up this equation to get this far. Okay, and do you see that it's a quadratic? Pi is just a number, 3.14. So you have 10L, and then you've got L squares. That's just like an X and an X square. So you're going to have a parabola that works there. All right, so if you wanted to get a common denominator there, you got 10L minus L squared over 2. Pi over 4 is the same thing as 2 pi over 8. So you've got minus 2 pi over 8. If I was just getting a common denominator there to go with this one. L squared plus 1/8 pi L squared. This looks worse than it is. I hope you're not thinking this is too bad. Are you thinking it's bad?
Yeah.
No, you're not. All right, but now it's looking good.
You're off the screen.
I'm off the screen. Okay, I just got a common denominator between those two terms right there. If you just put that in your calculator, you can get your coefficient. But that's enough to show you that you got a negative in front of your L squared. You got a parabola that's going to open down. So if you can get to that vertex, you're going to be able to get to your dimensions to maximize your area. All right, let's take it from the top, because I'm running out of time, to make sure we can get to the setup. You had a perimeter, and you expressed that. You had to express the area of a rectangle and a half of a circle. You had to get it all in terms of the same variable. And once we saw for W, we put it in there, and that's when things started looking a little scary at first, but it's really not. In fact, if you just had your graphing calculator, you could plug it in and get a nice little picture. But once you got here, if you use like 3.14 for your pi, then those are similar terms. And then you can find the vertex, and you would know how to maximize your area. Okay? All right, we have another problem to do, a couple more problems from this section to do next time. But next time, we are also going to go to a supplement, which is called regions bounded by curves. This is a very calculus-related concept. So if you're doing this by video, this will be on your website for you to get a copy of. And what I'm going to do to you guys is pass this out because you want to go ahead and sketch the curves, shade the bounded region. Okay? So go ahead and sketch the curves like all of number 1 would be on the same coordinate system. And these curves are going to intersect. And you're just going to look for that little region bounded by those curves. And we're going to pick up on that also at the next class. Okay, make it a great day, everybody.